Example 17. Last example in the notes that is dealing with titrations for now. And we'll get into the practice packet. With example 17, it says a solution of 0.1 molar HCl and a solution of 0.1 molar NaOH are prepared. A 40 milliliter sample of one of the solutions is added to a beaker and then titrated with the other solution. So if we think about it, we have one solution in the beaker, the other is in the burette, and it's being added into the beaker. A pH electrode is used to obtain the data plotted in the titration curve shown at the right. So part A says identify the solution that was initially in the beaker and explain your reasoning. So we are looking at the solution that was in the beaker right here. So when 0 milliliters of the titrant, that's what's in the burette, so we think about what's in the beaker. Here's the setup for the titration. We have the titrant, and we have the analyte. It's asking us what the analyte is. So we can take a look at the starting pH. We know that we have two options. We have HCl and we have NaOH. So we either have a strong acid or a strong base. It's asking us what are we starting with. So if the pH is about 1, what's going to be in the beaker? The acid. Right? The acid is going to be in the beaker because a pH of 1 is acidic. So we'll say the solution in the beaker, 0.100 molar HCl, because the initial pH is 1. So it wanted us to identify and explain. So we identified by saying the solution was the HCl, and we explained by saying the initial pH is 1. Low pH means we're starting with an acid. Part B says, on the titration curve at the right, circle the point that corresponds to the equivalence point. Remember, the equivalence point is about halfway up the vertical line. The equivalence point is about halfway up the vertical line. I'm going to circle this point right here. Now this also should make sense because in a strong acid, strong base titration, the pH at the equivalence point is 7 because the salt that is formed is neutral and water is neutral. Part C, at the equivalence point, how many moles of titrant have been added? So we know that this was HCl, which makes the titrant what's in the burette, NaOH. Now what I like doing before any calculations is I'm going to focus on where I'm at here. Equivalence point. I know at the equivalence point that moles of acid equals moles of base. That's the definition of the equivalence point. Moles of acid equals moles of base. So the moles of HCl equals the moles of NaOH because the acid has been completely neutralized. When we look at the titration curve, because the titrant is NaOH, so I know that we have 0.1 molar NaOH, because that's what it said. We had 0.1 molar NaOH in the burette. Then at the equivalence point, 40 milliliters of NaOH was added. So if we know the molarity and we know the volume, we can find the moles. The titration curve not only shows us the pH at the equivalence point, but it also shows us the volume added. I'm going to say 0.1 molar NaOH is X moles over 0.040 liters. Molarity is moles over liters. So if I multiply these, I get 0.004 moles of NaOH. This is actually a sample for your response question, so you can see how some of it is conceptual, other is math. Typically, the calculations that they will have you do is looking at the equivalence point, or if you have a weak acid or base, looking at the half equivalence point. Then part D says the same titration is to be performed again, this time using an indicator. Use the information in the table at the right to select the best indicator for the titration. Explain your choice. So we have 3 indicators. We have methyl violet, methyl red, and alizarin yellow. So we have to figure out which one of these has a pH range closest to the pH of the equivalence point. Now your indicator won't always have the pH at the equivalence point exactly in the range. And if that's the case, you want to pick the one that's the closest. So if you look at these 3, I say, okay, I know the pH at the equivalence point is 7. Which of these indicators can I pick that will have a change closest to 7? I'm going to pick methyl red. So I'll answer the question up above here. I will say methyl red will be the best because it changes color. Closest to the equivalence point pH. So methyl red will be the best because it changes color closest to the equivalence point pH. The most ideal indicator would be the one where it changes its pH range, has the equivalence point pH in that range. But if it can't be in that range, you want to pick one that is closest to the pH of the equivalence point. So then if we look at part E, part E is more of a conceptual question, and it says, what is the difference between the equivalence point of a titration and the end point of a titration? A lot of times these words sometimes get used interchangeably, but they are different. Equivalence point is what we've been focusing on. That's when we can use stoichiometry. End point is based solely on an indicator. I didn't write this word. So we'll actually just look at the 2 definitions. So equivalence point versus end point. So the equivalence point is the point in a titration where moles of titrant added is equal to the moles of analyte. So the equivalence point, that's like the stoichiometric equivalence point. It's the point in a titration where the moles of titrant is equal to the moles of analyte. So we say it's the moles of acid equals the moles of base. The end point is the point in a titration where the indicator changes color. So if we are doing a titration and we don't have an indicator, we're not going to see an endpoint. If your indicator changes color in the same range in which your pH of the equivalence point is, your end point and equivalence point should be at about the same time. But equivalence point, we can think about this. Equivalence point is more quantitative. End point is more qualitative. A lot of times, chemists will use the end point to just determine about the volume of titrant needed, and then they will go back and they will use that information to actually do a more precise titration in which they find the equivalence point. And then part F, sketch the titration curve that would result if the solutions in the beaker and burette were reversed. So now that means that we're looking at the HCl being in the burette. And the NaOH being in the beaker. So on our titration curve, the y-axis is pH. Our x-axis will now be volume of HCl added. So before any HCl is added, we have NaOH in the beaker. We would expect it to start at a pretty high pH, somewhere probably between 12 and 14. And then really we'll just see pretty nice S-curve. The pH at the equivalence point will still be 7. I would say in terms of starting and ending, the pH up here should be between 12 and 14. The pH that you're ending at down here should be between 1 and 2, or maybe just less than 2. You're starting with a strong base. You're ending with a strong acid. The pH at the equivalence point will not change. The volume of HCl at the equivalence point will be 40 milliliters as well. Because if we looked back, they were the same concentration. So if they are the same concentration, they require the same volume to achieve the equivalence point. So if we had 40 milliliters of NaOH in the beaker, we would need 40 milliliters of HCl added. So this is example 17. You can see how this was a sample free response question. This one was mostly conceptual, thinking about what's happening in the titration. Questions on this example?